Okay, so hello everyone. So this is the second talk on higher categories. So Walker is going to tell us about, I suppose, concrete constructions in quasi-categories. Okay,
Yeah,
please take it away.
thanks very much. So yeah, this is a continuation of my talk from 2 weeks ago. And since the goal is to introduce at least some of the way that we actually work with quasi-categories and how some of these constructions are really defined and how their properties are proven, today we're going to be looking at slice quasi-categories. And so we're going to go through both the definition, how we define slice quasi-categories, and we're going to look at some technical properties. And in looking at these technical properties, we'll actually go through some proofs that I've chosen to hopefully be not too technically monstrous, but that will give some sense of the kind of technical arguments that arise when verifying properties of new quasi-categorical constructions. So we want to understand slice quasi-categories. And so the first thing that I'd like to do is take a one category, and so X, an object of C. And since I'm now tending to think of things as simplicial sets, I'm usually just going to use a subscript 0 to denote objects even when I'm dealing with a one category. And we want to try to understand simplices in the nerve of the slice of C over X. So fortunately, we can just write these down. A zero simplex in the slice is just the same thing as some object y and some morphism y naught to x in C. And a one simplex in the slice is going to be, well, we have two of these objects, y naught and y1, f naught, that should be a 1, x, and we have a morphism which I'll call G01, such that this diagram commutes, once again, in C. And a two simplex is going to be three such objects, y0, y1, y2, f0, f1, f2, morphisms G01, G12, G02, such that everything commutes. And we can continue so on and so forth, constructing simplices in this slice, but already we're seeing a pattern emerge. And that pattern is that a simplex, let's say an n simplex, in the nerve of the slice of a one category is an n plus 1 simplex in the nerve of C with terminal vertex x. Same thing. And this is the definition that we're going to try to make for the case where C is a quasi-category rather than just the nerve of a one category. But before we do that, let's think a little bit about why this is a not crazy thing to do, right? Quasi-categories involve much more coherent data, and so it's not immediately apparent that just doing the thing that you would do with a one category is fully justified. So I'll explain the reason that I think that this is justified in two different ways, one that's a little more technical and one that's a little more intuitive. The intuitive thing is that when we would be considering diagrams like this in a quasi-category, these no longer become commuting triangles, they become specified data. And so these become, for instance, two simplices, three simplices that imply a certain amount of coherence being built in to our definition. The more formal way of putting that is in the Joyal model structure, in the model structure for quasi-categories, every object is cofibrant. And that means that the mapping space out of any object, so long as the target object is fibrant, that is a quasi-category, is going to be the correct mapping space. And so, in some sense, saying, oh, we're taking maps from something into our quasi-category is fine, because that's going to have coherence, this additional coherent data baked into it because of this property of the model structure. So now that we have some understanding of how we want to define this slice quasi-category, we're going to try and make a more general formal definition so that we can define slices more generally and some technical tools that we're going to make use of in later work. So the definition that I want to make is the following. Given x and y, any simplicial sets, the join of x and y is the simplicial set x star y that has n simplices defined to be the coproduct, disjoint union, over I plus j is equal to n of xi times yj, where I or j can be the empty set, and by convention, x empty is the point, is y empty. Side note, is anyone unfamiliar with the ordinal sum that I'm using here? Okay, so the ordinal sum, well, these things are just ordered sets. And so we can create a new ordered set just by sticking them next to one another. 0 less than 1 less than I, less than 0 prime less than j prime. So this ordinal sum says take this first ordinal and then put the second ordinal after it and treat that as an ordinal. So it's worth noting that the non-symmetry of this procedure is why this join is also not symmetric, right? It matters that we have I first and then j, not the reverse. So let me give an example. Let's say that x and y are both one simplices. And let's think about what the join does. Well, when I is the empty set, we're going to get a copy of y as our simplicial subset. And when j is the empty set, we'll get a copy of x. But then, for each pair consisting of a 0 simplex in x and a 0 simplex in y, we're going to get a 1 simplex in the join. And then for each pair consisting of a 1 simplex in one and a 0 simplex in the other, we'll get a 2 simplex. And for the pair of 1 simplices, we'll get a 3 simplex. So the join here really is just the 3 simplex. And more generally, we have that delta n join delta m is isomorphic to delta n plus m plus 1. Now, for those of you who are more familiar with, say, one category theory, you can also think of the join as the monoidal structure on augmented simplicial sets that comes about via deconvolution along the ordinal sum. That will not be important to anything else I say today, but if that is the perspective you're coming from, it can be a convenient perspective to use. So it's also worth noting that the join, say with x, so blank join x, defines a functor from set delta to set delta x over. So the category of simplicial sets equipped with a specified map from x. And this has a right adjoint. So this tells us that this join operation doesn't really preserve colimits per se, but it does preserve colimits into this thing. And so it does have an adjoint. Okay. So now that we have the join, we can actually make a more formal definition out of our intuition from the one categorical case. So we can say definition for a quasi-category C and X, an object, the slice is the simplicial set C over X defined by hom from delta n to C over X is hom X from delta n star delta naught to C. So what do I mean by this? Well, firstly, let me unpack the notation and then let me say a little bit about what I'm doing here. This hom superscript x is those maps of simplicial sets from delta n star delta naught to C, which send this delta naught precisely to the vertex x. And so you can think of this, if you like, as the hom in one of these slices, where this slice, this capital X, is now just a copy of delta naught. And you have the map from delta naught to C that includes X, and you have the canonical inclusion here, and then this is just the hom in the slice. Now, what this is doing is turning into a definition our previous intuition. What this is saying, we define a simplicial set by defining its sets of n simplices. So we define its set of n simplices to be precisely the set of n plus 1 simplices that send the terminal vertex to X. Everyone okay with that? Okay. Before moving on to actually starting to say things about this, let me give a generalization of this definition, which will be a technical tool we use later. No, and in fact, that's the next thing that I'm going to prove. Yes, it's not immediately obvious. It requires some argument. Yeah. Other questions? Okay. So, yes. Okay, yes. So there's a generalization. Given X to C, F, a map of simplicial sets, define C over F by exactly the same formula, just now hom from delta n to C over F is hom F delta n star X to C. So these are now the maps that restrict to F on X as a subset of this join. Same basic definition, we're just saying now we can put anything there. I should also point out here, there's a canonical map pi from C over X to C, which sends a map from delta n star delta naught to C to that map just restricted to delta n. You can project down to the original quasi-category by forgetting this final vertex. Okay, so now we have the pieces in play to answer Ergen's question, namely, yes. Yeah. And those are more complicated to define. Today, I'm really only going to be talking about slice category, over and under categories, really. Yes, yeah. You can, basically any one categorical construction, any reasonable one categorical construction, you can mirror in quasi-categories or really in any model for infinity categories. It's just that some are more technically challenging than others. To some degree, I am choosing the topics that I'm presenting a little bit carefully so that I can show some technical arguments, but not like multi-lecture proofs. So the lemma says if C is a quasi-category and X is an object, then this slice fibration, this map from the slice to C, has the right lifting property with respect to lambda ni to delta n for all 0 less than I less than or equal to n. So this is actually stronger than the lifting properties that we were considering when we defined quasi-categories, because it includes this n. It allows you to lift horns of, say, this form, outer horns, and to fill these to something like this. So this will then imply that this slice is a quasi-category, because in particular, this map has the right lifting property with respect to the inner horns, as does this map, and so this map will as well. So let's prove that. We want to solve the lifting problems, lambda ni to delta n to C. So we want to show the existence of this dotted arrow. Whoops, no. What am I talking about? We want to solve a completely different lifting problem than the one I just wrote down. This is the one we want to solve. So what we're going to do is we're going to use the fact that we defined this slice quasi-category via a junction to pass to what's sometimes called the adjoint lifting problem. So what is this? Well, we notice that this top map from lambda ni to C over X is going to be the same thing as a map from lambda ni join with delta naught to C. Everyone okay with that? And then this bottom map from delta n to C is the same thing as a map from delta n join with the empty simplicial set to C. And then the fact that this diagram commutes mean that both composites down to here agree. And this map is just going to be a map from lambda ni join with the empty set to C. So the data of the outer commutative square can be reformulated as a map like this. And then what we want in a lift is a map from delta n to the slice. But we know that that's equivalently a map from delta n join delta naught. Let's keep that dotted, to C. So equivalently, instead of solving this lifting problem, we can solve this lifting problem. And this is a quite general framework. In fact, you can define this a little bit more generally, where you have a lifting problem here that's C to D, and then you have both, you have three maps involved in passing between adjoint lifting problems. But if, for instance, you study monoidal model categories, these adjoint lifting problems show up a fair amount. And in fact, very particularly, this sort of construction where you have this monoidal product and then a push-out, which is called a push-out product, ends up showing up quite a lot in the study of monoidal model categories. It's quite an important technique. So we pass to the adjoint lifting problem, and now my claim is that we can solve this adjoint lifting problem, which is good enough. Now, why do I claim that? Well, the first thing to notice is that this bottom thing is just delta n plus 1. And so I'm going to try to identify this top thing with something we understand a little bit better. So let's ask, let me call this top thing something. Let's call this Z just temporarily so that I don't have to keep rewriting it. So which n simplices of delta n plus 1 live in Z? Well, here in lambda ni join delta 0, we have some missing n simplices. We're missing the ith face, of course, because that would be the ith face here joined with delta 0. And we're missing the n plus 1 face. And then here, is, the n plus 1 face. So we have all of the faces except for di. That means that Z is just lambda n plus 1 I. And since we assumed that I is strictly greater than 0 and less than or equal to n, this is an inner horn. And so we can solve this lifting problem because C is a quasi-category, and we're done. Now, I should say, once again, this is an uncommonly straightforward version of this kind of argument. Usually you would have to do some sort of more serious combinatorial argument to this morphism to show that you can, in fact, create such a lift. But in this case, it works out quite nicely, and this tells us, yes, the slice quasi-category is, in fact, a quasi-category. It tells us a little bit more than that. It tells us that this map has a pretty strong lifting property. And we're going to give that lifting property a name in a moment. But first, let me briefly talk about the dual version. I should say, as before, please feel free to interrupt me if anything is unclear or confusing. This is a complete proof, yes. Oh, no, I'm saying more generally when we're making this kind of argument for different constructions. Yes. I chose this construction because a number of the proofs are actually quite short and nice. There are a number of push-out product type axioms that you can prove that require some fairly extreme combinatorics to get through. All of the ones that I'm going to talk about today do not require that sort of extreme combinatorics, but one thing that I will, or two things that I will state without proof, do. So the dual version is we can define Cx over the other slice just by reversing the direction of the join. And the way in which these are dual is a little bit specific. We can define an opposite quasi-category, which again, we'd like to have because we can define opposite categories and we'd like to be able to make duality arguments in this setting. So let R from delta to delta be the automorphism which reverses order. So what do I mean by that? Well, let's say we have some morphism in delta. This is going to be sent to the thing 0, 1, 2, 3, 0, 1, 2, where we're trying to flip the order of both of these sets. So we get, this is like 3 prime, 2 prime, 1 prime, 0 prime, 2 prime, 1 prime, 0 prime. And so now the morphism that we have is reversed. Define for x in simplicial sets the opposite simplicial set x op to be just x composed with this order reversing automorphism. Just think of this as reversing all of the directions of all of your one simplices, if you like. That's effectively what this is doing. So then we have that C op x over is isomorphic to C over x op, exactly as with one categories. And that just amounts to untangling each of the definitions, seeing what this op does to the join and how it plays with our definitions. Okay, so with that in mind, I want to turn this lifting condition into two definitions that are dual to one another. We say that let's say that pi from x to y is a morphism of simplicial sets. Pi is a right fibration, which I'll often abbreviate as RFib. If for any 0 less than I less than or equal to n, we can solve this lifting problem. So this lift exists. And as an example, we have c over x to c. Dually, we can say pi up from x to y is a left fibration. So this is if for all 0 less than or equal to I less than n, lambda ni delta n to y op, pi op from x op to y op, this lifting property holds. And an example is c x over to c, the other slice vibration. And the way that one sees these are dual is just computes what passing to opposites does to the horns. And one can fairly easily check that lambda ni op is isomorphic to lambda n minus I. And that's why the only thing that changes is which of these is less than or equal to. This right horn becomes a left horn, if you like. So far, so good. Everyone okay with the definitions thus far? And also, how much time have I used? Okay, plenty left. So, in that case, let's try and give a reason why this is a good definition. And I should say, this is going to be the first of those two statements that I said I'm not actually going to prove because the proofs are extremely long and technical. Why is this the right definition? Well, I've already motivated it somewhat. I've shown that it agrees with what you get in the one categorical case, which is definitely something that you want. But there is another property that we would expect of these slice vibrations, namely, if C is a one category, we have that the following diagram is pullback. We have the Hom set to C over X to C to the terminal category Y. So that is the fiber of C over X to C over Y is the Hom set, CYX. And so if C is a quasi-category, we can define, I'm going to follow the notation of higher topos theory, map R, C, Y, X. We can define this to be the pullback, C over X, C delta naught Y. So the same fiber. And then from there, we have the following theorem, which, if I remember correctly, was first proven by Joyal and then proven again differently by Lurie. If C is a quasi-category, there is a natural weak equivalence map in C right yx to the mapping space in the rigidification of C from y to x. So this tells us that in the homotopical sense, this other property that we would expect of slice categories still holds in the quasi-categorical setting. That is, the mapping spaces, which we initially defined to be these mapping spaces in the rigidification, really do form the fibers of our slice fibration. So this statement is quite nice, and it gives us an alternate model for our mapping spaces. Now, one might ask, why do we need an alternate model? This is one that is perfectly good, somewhat computable, and part of this Quillen adjunction that we used to understand our model structure in the first place. And the reason is, these things are not in general fibrant. These aren't concomplexes. However, these are, and that's the next thing that we're going to try to show. Yes, and in fact, that is what we're going to show. If you have a left or a right fibration, I mean, we're only going to work with right fibrations because the theories are exactly dual. It's worth noting that concomplexes are, of course, a self-dual subcategory precisely because of this thing that I just erased about horns. But yes, that's what we're going to show. So I should also say we can draw pictures of the simplices in here. The zero simplices are just going to be what you'd expect. The one simplices are going to be again, more or less what you'd expect. The two simplices are going to be once again, more or less what you'd expect, and so on and so forth. So it really does look like this is what you would expect a mapping space to be, right? A one simplex is going to be a pair of morphisms and a homotopy between them, however you want to define that. And a two simplex is going to be a trio of morphisms and coherent homotopies among them. Okay, back to regularly scheduled programming. So the way that we're going to try and understand why this guy here is fibrant is we're going to look at equivalences in a quasi-category. And along the way, we're actually going to prove a statement that last time I made without proof, but that today we're going to be able to actually give an argument for. Namely, that if you have a quasi-category and all of its morphisms are equivalences, then it's a concomplex. So this goes back to this motivation that I was giving before, namely that concomplexes should be infinity groupoids, and that's exactly what we're going to show along the way. So let's define. Let C be a quasi-category, a morphism f from x to y in C, so that is a one simplex, is called an equivalence if it represents an isomorphism in either the homotopy category of the rigidification of C, or equivalently, this fundamental category functor applied to C. So I would very much encourage you to, yes?
Sorry.
Yeah, please.
Now I'm just going to, so what is inside the hole?
The rigidification of C. So the basic idea is we have this commutative diagram cat to simplicity enriched categories to, let's stick with set delta. Here we have the nerve, here we have the homotopy coherent nerve, and here we just have the inclusion. And this diagram commutes. And all of these have left adjoints. C, the homotopy category, and what I called tau1, the fundamental category functor. And so as a result, the corresponding diagram of left adjoints commutes. And so that tells us that Ho of C is the same as tau1. Now, what does this mean explicitly, that something in a quasi-category is an isomorphism in tau1 of C? Well, it means that F is an equivalence if there exist G and H such that, or actually, let me, instead of saying that, let me just say what it means for F to have a right inverse. G is right inverse to F if there is a 2-simplex X. So this is our 2-simplex sigma in C. And what do I mean by ID Y? Well, this is just the degenerate 1-simplex on Y. So one can show this, for instance, by giving an explicit characterization of tau1 when C is a quasi-category. And in that case, one sees that since C is a quasi-category and has these nice lifting properties, you can actually take tau1 of C to have objects, the objects of C, and morphisms, equivalence classes of 1-simplices in C under the relation that 2 1-simplices are equivalent if they form 2 edges of a degenerate 2-simplex. When I say degenerate, I mean having the identity as its third edge. It's not actually the image of a degeneracy map. Otherwise, we'd be defining F to only be equivalent to F. Anyway, left or right degenerate, let's say. Anyway, is everyone okay with this? Okay. So the first thing that I want to do is prove a lemma that gives 2 simple properties of how equivalences interact with right fibrations. Lemma, let F from C to D, bless you, be a right, bless you, between quasi-categories. then 1, no, let's call this pi, and let f, no, 1. Let f from x to y in C if pi of f is an equivalence, then f is an equivalence. And then 2, let x be in C naught and f from pi of, y, pi of y, f from x to pi of y, an equivalence in D. Then there exists an equivalence f tilde from x tilde to y in C lifting f. Everyone okay? I see a little bit of consternation at the second statement. This is a right vibration throughout this whole. There's no right. So somehow the interesting thing about this is not a right horn. This is a left horn. There's no condition. Yes. Well, if you change to a left vibration, you have to reverse the direction of all of the arrows. That doesn't change the first statement, but it does change the second statement. Yes, the second statement is directional, right? It's about the target of this morphism rather than the source. But if you switch to a right vibration, or sorry, a left vibration, what you're actually doing is passing to opposite quasi-categories. And so you need to alter that. Now, it's also true that just the dual statement holds immediately, because then you're just lifting a right horn. Okay. So, yes. I have a question over there. Yes. Clarified something kind of I clarified something that is confusing. That's the usual way I speak. Please. Yeah. No, so if C is a quasi-category, the morphisms of tau 1 of C is the set C1 modulo an equivalence relation. And this equivalence relation is F is equivalent to G if there exists either F, G, a triangle like that. What is the right-hand edge? The identity, the degenerate edge. Or but what is the connection to the right? Why did you define the right inverse? What was the context? Oh, this definition, one of the ways to see that this definition works is by working out really explicitly what tau 1 of C is in this way. One of the ways to see that this follows from this definition. I was giving an aside saying you can write down this definition. When C is a quasi-category, you can explicitly describe tau1 of C in the following way. And then, given this definition here, that something is an equivalence if it becomes an isomorphism in tau1, you see that it has to have left and right inverses of this form. Yeah. Okay. Other questions before I continue with the proof? Okay. So, to prove statement 1, this turns out to not be too hard. So, let G be a right inverse for F. So we have in D, pi of F. We have in D this 2 simplex, where this is X, Y, Y. And, well, these are pi of Y, pi of X. And in C, we still have degenerate simplices, and we have F. So this is forming a lifting problem, a lambda 2, 2 to delta 2. Because this is a right vibration, and this is a right horn, this means that we can fill this, and we get some G tilde, which is right inverse to F. However, we can do this again, right? Since G is right inverse to an invertible thing, it is itself invertible. So if we do this twice, find that G tilde has a right inverse. So G tilde is an equivalence, and so F is an equivalence. So what we do is we say, we start with this F, we show that it has a right inverse, we show that its right inverse is invertible, and that means that it is invertible. Okay, and then I'm actually just going to get rid of this argument so that I don't have to move to a different board. So now, let's suppose that we have this setup where where Y maps to something that is the target of some equivalence, and we want to lift that equivalence. So choose inverse G, right inverse G, right inverse, left inverse. Maybe I want a left inverse. We'll see. Left inverse G from pi of Y to X to F. Well, then we can form the lifting problem. So here is, once again, D, here's C. We can form G from, actually, let me write this, X, and here we have just Y. Now this is lambda 1, 1, so an outer horn. This is delta 1. And so once again, we can complete this, solve the lifting problem, to get g tilde from y to x, which lifts g. And then we can form another lifting problem. Namely, we have pi of y, g, f, x, we have the simplex that displays g as a left inverse to f. And here, well, once again, we have the identity on, whoops, this should be an x tilde, pardon, x tilde, y, g tilde. And once again, this is a lambda 2, 2 to delta 2, and so we can solve this lifting problem to get f tilde. So we've constructed a morphism that lifts our f as desired, and by part 1 it's an equivalence, and so we're done. It maps to an equivalence, so it is an equivalence. Questions? Yeah.
Confused about the first one.
Yeah.
So the right means which side is included? Is it the right hand?
Right horn means that you...
When you generate x tilde, is it the right direction? I would use that. Right vibration implies that the so one of the endpoints is supposed to be included in the order. That's the
Lambda. I might have screwed this up. Maybe I need to take a right inverse. Let me think for a moment. Yeah, because, no, so lambda 1, 1 is the set containing 1. You forget the one face, which is 0. So this is backwards. Yeah, this should probably be a right inverse. My apologies. In which case I also wrote the proposition backwards. Okay. This is what I get for rushing. F I y to x, yes, and then that's the correct 0 horn, y to x tilde. So I gave the dual argument for the dual statement. I'm not going to, yeah, if I changed it to left vibration, everything would have worked. Sorry about that. That was quite sloppy of me.
yeah, but yeah, I think the idea of
Yeah, okay. Yeah, and so again, it is the correct argument. You just have to reverse all of the arrows. Okay, so we're going to use this lemma to prove a more complicated proposition. And this proposition and its dual will give us the statement that we're looking for. So, proposition. Let C be a quasi-category. Then f from x to y in C is an equivalence if and only if the lifting problem or let's say every has a solution. So what is this saying? Well, in the case when n is 2, what we're saying is that we can define a right inverse to f. No, a left inverse, sorry. A left inverse to f. And then the higher versions are coherent versions of that. The idea is somehow if we have a diagram like this, where, 0, 1, 2, 3, where this is an equivalence, we should be able to invert this equivalence formally and fill in the back face of that 3 simplex. F, this would be F, 0, 1. Oh, whoops. I see, yes. So what this is saying is the restriction to this edge of this horn has to be F. So there's a dual version of this, which will also hold. C is a quasi-category if and only if C op is a quasi-category. And so the dual version says here we have instead n minus 1 n. Here we have lambda n n. Here we have delta n. So we're not going to prove the if and only if statement. We're going to prove, No, we're going to prove the other direction. So I'll leave it as an if and only if. What this tells us, though, is precisely this statement that we had mentioned before. Namely, if every morphism in C is an equivalence, then C is a concomplex. That is an infinity group. And the reason for this is if every morphism in C is an equivalence, then this tells us that you have the lifting property against all left horns. This tells us that you have the lifting property against all right horns. And you already have the lifting property against all inner horns because it's a quasi-category. And so it follows that this is a concomplex. Everyone okay with that? And then the further corollary is that fibers of left fibrations and right fibrations are complexes. And the reason for this is the fiber of a left fibration is a left fibration. So if we have C to D left fibration and some fiber, E, then this is a left fibration over the point. And everything here is an equivalence, which means, by our lemma, everything in E is an equivalence. Which means, by our corollary, E is a concomplex. Any questions before we move on to more technical matters? Yes, that is the more technical matter it requires a bit of a digression and a little bit of technology. That's why I want to pause here and ask. So far, so good? Okay. So let's now try and prove this proposition. And the first thing that I'm going to do is prove a little helper lemma. If C is a, let's say C is a quasi-category, M is bigger than or equal to 0, N is bigger than or equal to 1, and 0 less than I less than equal to N, then C has the right extension property with respect to the push-out product, delta, do I have this in the right order? Let me check. Nope. Lambda ni star delta m coproduct, lambda ni join boundary of delta m, delta n join boundary delta m, to delta n join delta m, delta n plus m plus 1. So this is a purely technical statement, again involving one of these push-out products. But again, it's not going to be too bad of an argument. So once again, we're going to ask which n plus m simplices do we have? In lambda ni star delta m, we have the simplices d naught through di minus 1, di plus 1, dn, and in delta n star boundary of delta m, we have dn plus 1 through dn plus m plus 1. So this is lambda n plus m plus 1 I to delta n plus m plus 1. And again, the proposition is proven. So once again, a warning, in most of the cases when you're considering push-out products, things aren't going to be as nice and immediate as in these. So from, yeah? Yeah.
Would you just define a map on the missing simplices and check the
yeah, so typically what you would do is, let's say you have a smaller simplicial subset. Let me just show what you would do if you wanted to show that this inclusion that I've drawn here could in fact have the correct lifting property. Right? This is no longer just a horn, it's a little more complicated. Well, what you do is you factor it. you factor it through this thing, where now we have these three faces, but not that bottom face. And the way we do that here is we're taking a push out against an inner horn inclusion, this inner horn inclusion. So we can do that because it's an inner horn inclusion. So we take that push out against an inner horn inclusion, and then this becomes an inner horn inclusion. And so I should say, once again, this is a very simple case of that kind of argument. Often you have to do many, many step versions of this, like push out by the things that you know you're allowed to push out by until you get the final product. So that's the kind of argument that would show up if it were something more complex. Other questions? So now we're going to need a tiny little bit of model category theory, but before we go there, I just want to mention a corollary of this statement. Passing to adjoint lifting problems, we get that the slice C, actually, for G from delta M to C, the map C over G to C over G restricted to the boundary of delta N is a right fibration. So whenever we're looking at these push-out products, we're really talking about when certain generalized slices, maps of generalized slices are fibrations. That's what this combinatorial side is really telling us. And so whenever I'm over here proving something about some push-out product, you should be thinking, okay, this is aimed at showing that some map of some kind of slice is an appropriate type of fibration. Yeah, so if you move the deltas and delta M's over into slices in C, this is the map that you get. If you want, we can go through and try to disentangle that at some point, but I'm not sure quite how much time I have, so I perhaps should, yes, I should get to the point. But afterwards, I'd be happy to discuss adjoint lifting problems more in detail. So, definition, a set S of morphisms in simplicial sets is called saturated if it contains the isomorphisms and is closed under coproducts, pushouts, retracts, and directed colimits. I should say directed colimits, closed under directed colimits, that's sometimes called closed under infinite composition or closed under countable composition. We denote the smallest saturated set containing S by S bar. And then we'll use the following facts from model category theory. Firstly, the set of morphisms with the left lifting property versus some f from x to y is saturated. 2, and this is more or less immediate from the definition, the intersection of saturated sets is saturated. And 3, the smallest saturated set containing all of the boundary inclusions is the monomorphisms. That is, the injective maps of simplicial sets. So now using that, I'm going to claim the following. The set of maps f from x to y such that for all 0 less than I less equal n, and for all quasi-categories, the push-out product lambda n I star y push-out over lambda n I star x delta n star x to delta n star y has the left lifting property with respect to f. Actually, let's say pi. Sorry. I was right the first time. With respect to c, is saturated. I am not assuming anything on F. I'm just saying the set of those maps of simplicial sets that have this property is a saturated set. We're not going to use all of these facts in that proof. We're going to use all of these facts either in the proof or in getting corollaries out of it. So, well, because the intersection of saturated sets is saturated, it's going to suffice to show this for one such horn and for one quasi-category, because then the set that we want is given by taking intersections over those horns and over quasi-categories. So since the intersection of saturated sets is saturated, it suffices to fix lambda n I to delta n and c and q. So we want to solve lambda n I star y coprod lambda n I star x to c. We can pass to an adjoint lifting problem where now we're moving the lambdas and deltas over to the other side. So this is equivalent to lifting this is C over This, this is C over, let's say for all f from lambda, from delta n to, sorry, for all g from delta n to c, lifting g, c, g restricted to lambda n I over, here's f. So we pass to the adjoint lifting problem. That's saying that we have these, for any map from delta n to c, we have these corresponding slices and this corresponding map of slices. And so this is equivalent to this adjoint lifting problem. So this is the set of f which have the left lifting property with respect to the morphism Cg over 2 Cg restricted to lambda ni over, and so this is saturated by part 1. So we just move over to the adjoint lifting problem, and we show that this set is saturated. Everyone okay with that argument? So let's derive a corollary. For any inclusion f from x to y, and for any c a quasi-category, any lifting problem lambda ni star y coproduct lambda ni star x delta n star x to c to lambda, delta n star y has a solution. How do we know that? Well, we know that that's true when f is one of these boundary inclusions, and we know that the set of things for which that's true is saturated, and we know that the smallest saturated set containing the boundary inclusions is the injections. And so I should have said injection here, just to be consistent. So that means that the injections have to be part of that saturated set. And so once again, this is just a statement that tells us something about the adjoint lifting problems. Okay, now we have the pieces in place to actually prove the proposition. So, proof of the proposition. We note that we can write lambda n0 as delta 1 join boundary delta n minus 2 coproduct over, let me double check so that I don't have to rewrite this. Yes. Oh. 0 join boundary delta n minus 2, 0 join delta n minus 2, 2, delta 1 join delta n minus 2, which is just delta n. So this allows us to pass from the lifting problem which we were considering, which for the ease of the camera I'll briefly rewrite. We had this delta 0, 1, lambda n 0, delta n, c, f, and I called this g, and we wanted. So the adjoint lifting problem, at least to the bottom, is going to be 0 to delta 1. Here we'll get c over g restricted to delta n minus 2. Here we'll get c over g restricted to the boundary of delta n minus 2. And then we have this forgetful map to c. This is going to be f. And this is going to be something that I'll call g tilde, because it is a map determined by the restriction of g. And so we know that this exists, and we want that. So from our corollary, we can pass to adjoint lifting problems and see that these are right fibrations. So suppose f is an equivalence. Well then, by the fact that this is now a one morphism in this thing that maps down to an equivalence in C, we have an equivalence here. But then this lemma that we proved and I've now erased says precisely that we can then lift that to an equivalence up here. So we can lift g tilde to an equivalence in C over g restricted to delta n minus 2, solving the lifting problem. So this now tells us that the proposition and our two corollaries hold. Now, if I have, do I have 5 minutes? Okay, I actually have 0 minutes. Let's just stop there then. Okay, thank you very much. Next time I'll be talking about limits and colimits using much the same technology we've been developing. Any questions? Yeah. Maybe here. Yeah, so how do you get the adjunction? Oh, the adjoint lifting problem? Okay, so I'm taking this and rewriting it as this monstrosity, this push-out product. Right. And I'm taking this and rewriting it as this. So now we move the delta n minus 2 over via the adjunction into the C. So if we just look at this part, 0 to delta 1 to C over G boundary delta n minus 2, C over G delta n. That is a terrible marker. And so now we can do the same unwinding that we did before. A map from here to here is the same thing as a map from delta 1 join boundary delta n minus 2 to C. A map from here to here is the same thing as a map from 0 join delta n to C. And then the fact that this diagram commutes means that they agree as maps from delta naught join boundary delta n minus 2 to C. And the solution is going to be a map from delta 1 join delta n to C. And so this bottom part of our lifting problem is precisely this bit. And then similarly, untangling, you can see that restricting to this copy of delta 1 gives you f in C, and so restricting to this copy of delta 1 has to give you f in C.
Wait, at the bottom, the join of delta 1 and delta n?
That should be n minus 2, sorry. Yes.
Okay, so the n's are n.
Yes, all of these places it's n minus 2s, here it's n, and here it's n, sorry. Yeah. So, yeah, there's this general framework where if you have a junction, you can pass to adjoint lifting problems. I mean, technically, you kind of need something sort of like a closed monoidal structure. Now, the join isn't actually a closed monoidal structure on simplicial sets, but it's close enough because it has this adjunction to the slice of simplicial sets. And so you can form these adjoint lifting problems that are equivalent, and that allows you to pass backwards and forwards between sort of like messy things on the right-hand side and messy things on the left-hand side. And when messy things are on the left-hand side, you can do sort of brute simplicial combinatorics to it to prove propositions. And when messy things are on the right-hand side, you can use facts that you have already established about fibrations, as we did here, to make your arguments. So I guess one side note that I would like to mention, because it will come up when we talk about limits and colimits, is that a right fibration is a trivial fibration, or trivial confibration, if you like, if and only if its fibers are contractible. And so what that means is that the right fibration C over X to C is a trivial fibration if and only if the mapping spaces into X are contractible, which is what we defined to be X being terminal. So this is a trivial fibration if and only if X is terminal in C. And this statement is proven using much the same sort of technology that we've been discussing so far, just a much more challenging combinatorial component. The push-out product that one has to study in that combinatorial argument takes several pages of argumentation to resolve. Okay.
Any other questions? Okay, so if not, let's thank Walker again.